All right, so today we're going to talk about chain rule. What's the chain rule do for us? Well, the chain rule will allow us to, it's just another weapon in our arsenal to find the derivative. We haven't run across this yet, but you will see that there are some functions that we don't know how to take the derivative of. So let's suppose I have this. We did a problem like this. Okay? You could do quotient rule, yes? You could split the fraction. You understand what I mean by split the fraction?
Yeah.
Yeah. This becomes x squared minus 6x to the negative 1. Then take the derivative. Or you could write it this way. Then that gives you another avenue. You could do that as a product rule, or I could distribute the negative 1 and get x squared minus 6x to the negative 1. Oh, looks. Wow, that was horrible. Stop it. Look, same. However, if that denominator function gets too scary, or it gets too complicated, this method will no longer work, so we need something new. And that something new is called the chain rule. In essence, what the chain rule is going to allow us to do is take the derivative of composite functions. What happens when we have a function inside a function? The biggest challenge for the chain rule is being able to recognize two things. How many functions am I working with, and which function is which? That'll make more sense in a second once I stop making brown or blue marks on the board. There we go. Okay, so you're going to need to be able to use the chain rule for composite functions. You're going to need to be able to simplify it. That's what's going to make some of you upset because it can get fairly complicated. I'll talk about the rules of that later. And then, of course, your friend and mine, the trig functions. And then last but not least, you should know the state capitals. Anybody know all 50? Okay. Good start. Not Chicago. Most people outside of Illinois think Chicago is the capital of Illinois, as do most people think New York is the capital of New York and LA is the capital of California. It's what?
It's Albany, New York.
Albany, New York. You know what California is? Sacramento. Very good. Okay. Jacob, you think you can do all 50?
All right, I'll try.
Rhode Island.
Providence.
Montana.
Helena.
Hawaii.
Hawaii. Honolulu.
North Dakota.
I wouldn't know if he was wrong anyways.
Pretty sure that's Pierre.
Which one did you give him? North Dakota?
Yeah.
What is it?
I thought it was
No, that's Bismarck. South Dakota's.
Oh, I stumped him. Yeah,
All right. Cool. Okay, so here's what the chain rule looks like. These problems, or these functions on the left-hand side, we've done examples of already, and you can do that without the chain rule. The ones on the right, under the column that says with the chain rule, require that you use the chain rule, because there are multiple functions there, or there's a composite function. So if we take that first function, the square root of x squared plus 1, how many functions make up that y equals?
2.
2. What are they?
Square root and a... What's that? Quadrangular?
Yeah, the quadratic. Correct. Okay. So we took that quadratic x squared plus 1 and put it inside the square root function. How many functions in the second one? Sine of 6x.
Isn't it one function?
No, there's 2 there. Yeah. 6x is one function, sine is the other. And then the third one, also 2 functions. Now you can see that of those 4 functions up there, we could actually do the third one without the chain rule. But that would require you multiplying out 3x plus 2 5 times. And nobody wants to do that. So we're going to use the chain rule. So here's the chain rule. I would use the bottom one. Makes a little bit more sense. We start with a composite function, f of g of x. And you want to think about these functions like onions. It's got layers, like an ogre.
Ogres. Huh.
What function is on the outside? What function is on the inside? And as the problems get more complicated, we can add more and more layers to it. We're going to start simple, but it will ramp up by the end of the lesson. When you identify the outermost layer of the onion, you take the derivative of that, and then you do what's called chain on the derivative of the inside function, or the next layer of the onion. This will make more sense when you see it in motion, but for now, that is the theorem, which in English, take the derivative of the outside function times the derivative of the inside function. And notice when you take the derivative of the outside function, you don't change the inside function. You leave it as is. Then you chain on the derivative of the inside function. Okay, so we're going to go very slow in these examples. I'm going to ask you a lot of, which would seem very easy questions, but if you can get these under control, it will make the more difficult problems a little bit more manageable. Okay? Are we okay so far? Got all this?
Yeah.
Good. As the problems get more complicated, you will get more functions. Functions within functions within functions within functions. You want to ask yourself, as it says up there, how many functions are we dealing with? You will chain on, always, without exception, chain on one less function. Okay? So if you've got 2 functions, you're going to chain once. If you've got 5 functions, you're going to chain 4 times. And you'll see why that's important, because it is conceivable that you can get a function where you could just keep chaining it on over and over again, and at some point you have to be able to rein yourself in so you don't go down some dark path and get a weird answer. And I'll show you what those dark paths / weird answers look like in a second. Okay. All right, so let's start with this guy. How many functions? 2. What are they?
It's a linear.
Yeah, the 2x minus 3 and?
Quadratic.
Yeah, well, close enough, yeah. The raised to the negative 2 power. Which one's on the outside of the onion?
Negative 2.
Negative 2. So we do the negative 2 first. Don't get caught up in what we're taking the derivative of. It's just some function. If I have any function raised to the negative 2 power, then the derivative would become, bring the exponent down, reduce the exponent by 1. Okay, so let me stop. Does that make sense? Again, don't worry about the 2x minus 3. It could be a smiley face raised to the negative 2 power. Negative 2 smiley face raised to the negative 3rd power. Now I need to chain. If there's 2 functions, I get 1 chain. So what am I chaining on? I'm chaining on the derivative of that function inside, which is 2. Then clean it up. That won't be an acceptable answer. In fact, we can do this now. As we start to simplify functions, there's 2 things you want to be concerned about. One is no fractions within fractions, and I think it's safe to say that you know how to deal with that. Second thing, no negative exponents. So an acceptable final answer here would be negative 4 over 2x minus 3 quantity cubed. But again, since we're just starting the chain rule, I'm more concerned about whether or not you can find the derivative. We'll worry about cleaning things up later. Does that make sense at all? This is the audience participation part of the program.
Yes.
Yes, good. I got 2 yeses. That's enough for me to keep going. Okay, you try that one. There are 2 functions there. Therefore, how many chains?
1.
Just 1. And don't bother simplifying it. Just take the derivative and leave it. Okay, we good? Again, don't simplify it because it's too ugly, but you should get a clicker that works. You should get that. Yes?
Yeah.
Okay. Bring the fourth power down, reduce it by 1. That's a common mistake, by the way. People forget to write that cubed, or that, cubed in there. Chain on the derivative of the stuff inside. And again, leave it alone. You can't simplify that because you don't want to multiply out a cubic. You could multiply that out. So you're taking a quiz, you're on the AP test, you have a total brain fart, and you forget how to do the chain rule. You won't, but you could multiply that bad boy out. But I don't think anybody wants to do that. We would then just use the chain rule and not put the answer up there. No different than the one before. Bring the 4 down, reduce the power by 1, chain on the derivative of 4x cubed plus 3. Does this seem manageable? Good. Anytime there's a function within a function, you have to do this. Now let's get to the nastiness. Simplifying derivatives. Sometimes, and it happens mainly in rational functions, the derivatives get really ugly. But again, 2 things you're concerned about. No fractions within fractions, no negative exponents. So try that one. And notice it says 2 functions, 1 chain. Your chain in this problem is going to include a quotient rule. That's where the funness really starts. That's fun, right? How we doing?
Lost.
Lost?
Yeah.
Okay. There's step 1. Bring the power down, reduce it by 1. Then chain. That big mess in the big honking parentheses on the right-hand side, all of that is the chain rule. What is that? That's a derivative of 5x minus 2 over x cubed minus 3. If you got to that point, great. You're done with the calculus. Everything from this point on then becomes algebra. Distribute the 5, distribute the 3x squared, combine like terms, and you get to that. 5 times x cubed is 5x cubed, and negative 3 times 5 is negative 15, minus blah, 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 blah. And then there's not much else you can do to simplify this other than you can combine your denominators and get that as a final answer. Because x cubed minus 3 times x cubed minus 3 quantity squared is x cubed minus 3 quantity cubed. How can we make it more complicated? I.e. more fun?
Negative exponent.
To start with? That'd be awesome. Anything else?
Like square root.
Square root would be fun. Word problem. Word problem would be really exciting. Other ideas? How about trig? Oh yeah. Here we go. You've seen that before. The only difference between what we've done already in this is that instead of using an x, I change the x to a u, which would be a function, and we chain on the derivative of that function. That's it. Everything else is the same, because now instead of being one function, sine of x, we have two functions, sine of x squared. Sine is on the outside, x squared is on the inside, chain rule, boom, done. Okay. So let's look at some more fun stuff, like this guy. How many functions?
2,
Nope.
3.
There are three. What are they? Christian?
Yeah. Sine.
Sine is one of them.
4x.
4x to the fifth, yeah, is 2. Where's the third?
Is that the squared?
Correct. Which one is on the outside of the onion?
The squared?
The squared is correct. Okay. So if there's three functions, how many chains? 2 chains? See what I did with that?
Yeah.
That's sick.
Trying to help your grade here, dropping money all over the floor? Must be dropping some bills there, Holmes. You know what I'm saying? 50 cents ain't gonna help.
50 cents.
Well, he might.
50 cents.
Get it?
Yeah.
Do you understand what I'm talking about? 50 cents owns his company.
Oh,
That's how he made most of his money. He owns Vitamin Water.
Really?
Yeah.
I love it.
He's a major investor. He's made millions upon, he's made more money from Vitamin Water than he's made from his illustrious rapping career. Are you saying he's not a very good rapper? I wish I had those kind of problems. Okay. So Christian, you said what was on the outside? The squared. So f prime of x. Bring the exponent down, reduce it by 1. Hold on, sidebar. You all know that this is the same thing as this, right?
Yeah.
Awesome, good. Okay, first chain. Talking about the onion again, we know that the squared function is on the outside. What's the next layer of the onion? Is it the sine or the 4x to the fifth?
It's sine.
Sine, correct. So now we have to take the derivative of sine of 4x to the fourth, which would be cosine, or to the fifth, I should say, 4x to the fifth. Let me get this out of the way. Last chain,
4x.
20x to the fourth. Done. Now, the reason why I've made such a big deal over how many functions and how many chains is because you see in a function like this, if you didn't know what you were doing and you got let off the leash, you could go crazy here. Oh wait, let's chain again. 80x to the third. And chain again. 240x squared. Oh, chain again, 480x. Chain again, 48. Chain again, 0. Oh, therefore f prime of x equals 0. That's crazy talk. You have to know when to stop the chains. And so in this case, 3 functions, 2 chains. This is gobbledygook. Doesn't make any sense. Stop after the 2.
There's 3 chains.
2 chains. 3 functions, 2 chains. Remember, it's always one less.
Looks like there's 3 to the way, right?
No, this is the first derivative. That's the derivative of the outer layer of the onion. Chain number 1. Chain number 2. 2 chains. Okay. Good? Problems? Can you handle this? Well, we'll see. It's going to be interesting and fun. Oh, I did want to point out one other thing. I included it here. Sometimes Bob will get a little fancies in it. Do you know who Bob is?
No.
Back of book.
Yeah.
Yeah, sometimes Bob will get a little bit fancy and start showing off his, he'll be flexing his math muscles, and you'll have some bizarre answer like this, and you'll be saying to yourself, self, how the heck did he go from this to that? And the answer will be that I just brushed it up against the board and it did that. And I've broken it. There we go, we're back. The answer would be that occasionally Bob will whip out some bizarre trig function that you may have forgotten about and got to there. I would be happy to stop here, but again, if your answer doesn't match the back of the book, that doesn't necessarily mean that, well, back of the book or answer key, depending on what you're looking at, doesn't necessarily mean that you're wrong. Okay. This is a summary of all the derivatives we've done so far. And we're pretty much done with derivatives. You have all the tools that you need to take derivatives. Now it's just a matter of practice, practice, practice. It'll also be some more applications of those derivatives, i.e. word problems and all the cool things that we can do with derivatives. Filling pools, crashing airplanes, crashing. A lot of the word problems involve death and destruction. I don't know why, but it always seems to work out that way. Falling off a ladder, cars crashing, trains crashing, planes crashing, 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 crashing.
We should check that out. Talk to the company, I don't know.
You think so?
Yeah, it seems a little sus.
Yeah, we should get some happier problems.
Yeah.
Like two kids on tricycles riding away from each other where no one's in danger of being injured. But it's always two people in a car heading towards each other, the same intersection. What time will they crash and die? You'll see when we get to those types of problems. It is fairly depressing, the types of things we'll look at. Okay. How long until the plane crashes, that kind of stuff.
Like someone's waiting on the railroad track. How long will two planes take
Right.
to crash into?
Right. Someone's riding on top of a train in a car. How long until the plane crashes into the back of the train while filling a pool? And then crashing the entire train into a giant lake.
Right. It's just an average problem.
Right. Where you can calculate the change in the rate of change of the frog population in that pond. Yeah. It's funny, we get to that exact problem later. All done. Okay? Questions, concerns, anything for the good of the cause? Outstanding. So like I said, a lot of this is practice, practice, practice. Get in there, get your hands dirty.
What is that? It's like 20 miles.
I don't know.
What's the square root of 600?
I just found that on the interwebs.
Way too fast for me.
What's the square root of 625?